Okay, so hello everybody. Thank you, Giuseppe, for the introduction. So this is Simone Romano. With Giuseppe, we work in the Dev Relations team at IoTeX. IoTeX is a blockchain-based platform. It's a tech stack where the blockchain is one of the layers that is designed to let's say, make it easy to connect real-world data with blockchain applications in a trusted and decentralized way. And basically allowing the creation of DApps. DApp stands for decentralized application that are based on real-world data. And we call, by the way, this type of DApps MachineFi applications. And then we will see why. I also want to mention that if any of you gets really interested into these topics, I highly suggest you to join our Discord channel, which is on the screen now, and where we have a community of other people learning and building on IoTeX. You can find me, you can find Giuseppe and the other team members there if you have any questions. And also, I also suggest you to register, just to log in. If you have a GitHub account, you can directly log in into the developers portal of IoTeX, where we are now adding more workshops and projects and demos and example codes that teach you about this MachineFi concept and also blockchain applications. So as Giuseppe anticipated, this is day 1 of 3, where the final goal is to build a simple MachineFi application that we will use as an excuse to introduce the concepts that are behind blockchain, behind IoT, the use of IoT with blockchain, and this concept of MachineFi. We will not really build the application line by line, but you will see the main parts that make this application. So in this first day, I will mostly introduce the concept of blockchain for those of you that are not familiar with this concept. Then I will introduce the IoTeX MachineFi DApp concept, and then we will start building this example of a work to earn DApp. Basically, it's a MachineFi application because it uses a device to generate data, working data, kind of a step counter, and it uses blockchain to reward. And so if you want to incentivize people to do this healthy activity in the real world. In the second day, we will take a closer look at an important component of this application, which is an off-chain or off-blockchain decentralized network, so a different decentralized network that we will see it's required to build these MachineFi type of applications. And in the day 2, we will also get our hands more dirty and actually send data from this device and see how this data is processed into this component and how it becomes ready to be ingested or used by smart contracts or blockchain applications. And finally, in day 3, which is in person, and Giuseppe will meet you in person in New York. He will take you through the actual blockchain application, so the smart contracts side of this MachineFi application, walk you through the logic, and then do the actual deployment of these smart contracts, and eventually put everything together. And you should hopefully see this application working for real, like doing steps and earning crypto tokens. So some prerequisites for this workshop, of course, not exhaustive in any way, because I actually advise you to dive deeper into this blockchain concept if you don't know about it and learn about this technology. There is a whole new world of things that can be built thanks to blockchain. So this is really a quick walkthrough of some concepts that may or may not make much sense to you. It's definitely not a 15 minutes introduction, maybe it's longer. So basically, what is blockchain? Blockchain is a distributed network. First of all, it's maintained by a decentralized network of nodes, anonymous nodes. We are talking about permissionless blockchain, so open blockchains to everybody. So it's maintained by a decentralized network of nodes, and each node maintains the exact same copy of what we call a ledger, which is the actual blockchain. So yeah, in this simple graphic, you see all the nodes of an hypothetical blockchain that maintain the same copy of the same ledger that makes the blockchain. Let's take a quicker, a little bit closer look at this, how this ledger looks like. So how actually the data structure of the ledger, what data structure we use for the ledger of a blockchain. So basically in a blockchain, you have a certain number of transactions because users of a blockchain wants to use the blockchain. They want to write data into the ledger. So they send transactions that bring some data, take some data with them, and want to store this data in the blockchain. And so the blockchain itself is basically a collection of transactions, and they are grouped into a data structure that we call a block that contains a certain number of transactions. These blocks are usually generated periodically, and each block is cryptographically linked to the previous block by including the hash of the previous block. We will see immediately after what is an hash, and eventually creating an ever-growing chain of blocks of transactions, and that's why it's called a blockchain. So one interesting thing of blockchain, so why it's so innovative, right? So it's not just a database, but the real innovation of blockchain is the consensus mechanism. So how all these nodes that are anonymous, that are peers, so there is no central authority, how they can reach a consensus on keeping exactly the same copy of this ledger, of this database, even taking into account what is called the Byzantine fault tolerance problem, right? Taking into account other nodes that can behave maliciously, or other nodes that can just not work entirely, or just not producing the correct outputs for this ledger. And so somehow proposing different versions of the ledger, right? How can this decentralized network keep the same exact copy of the ledger at any given time? And so the consensus mechanism is what makes this possible. And the most popular one is called proof of work, which is actually, to be more accurate, the proof of work is the way transactions are verified and what transaction do actually get selected in a block. And then the longest chain is the final consensus that decides which one is the actual version of the ledger. There are other consensus mechanisms that have been created after proof of work. The most popular ones are proof of stake, and one very popular lately is the delegated proof of stake. So basically, how does this thing work? Like I want to show you this live demo that I've used in the past. It's been built by this guy, Anders Brownworth. You can access it on his website. So very actually quickly, let me take you through these simple concepts so that we know what we are talking about here. So this is a live tool, very useful to explain these basic concepts, right? What is a hash? For those of you who are not familiar with a hash, the hash is usually called the fingerprint of a data. So if this is the data, and this is a hash that has been computed out of this data, you can see that for empty data, there is a specific hash, right? So if I add more data here, like Hi, I'm Simone. Okay, you see that the hash changes continuously every time I change the content of the data, but you will also notice that the size of the hash is always the same. Another interesting thing is that if I make a very small change in the input data, the hash changes entirely. So it will always be totally different, even if the input data changes only slightly. And as I said, doesn't matter how big the size of the data is, okay? The hash always has the same size. And of course, the most important property of a hash is that given a specific data, the hash that is generated from this data is unique. There is no overlap. So two different data will always generate two different hashes. And finally, given a specific hash, there is no way, as of today, if you use a good hashing mechanism, to get back to the data that generated that hash. So for all these reasons, the hash is often called the fingerprint of a certain piece of data. It doesn't matter how big the data is, it always will have a fingerprint in the form of a hash with these sites. So from this concept of a hash, you can move to the concept of a block, this data structure where the transactions, where the blockchain transactions are stored. Blockchain transactions are just messages, data messages that follow a specific message protocol that is defined by the blockchain. So here you again see a hash being computed out of data, but it's not computed on top of the data only, but also on top of two additional fields. One is the block number. Let's say we cannot change this because if we are computing a hash of a blockchain block, then this is the specific block number, the next block number that we want to attach to the blockchain. The data is also something that we usually cannot change because these are the transactions that blockchain users are sending to the transaction, to the blockchain. And so eventually there is this number here, the nonce, that is the very core of the consensus mechanism, of the proof of work consensus mechanism. So in the proof of work consensus, just by convention, it's said that a block is valid if the hash of the content of the block includes a certain number of 0 bytes in the beginning. So in this case, you see this block would be considered valid because it has 4 zeros in the beginning of the hash. And let's say that 4 is the minimum amount of zeros that we want for considering a block a valid block. So what it happens is that when I start including data in this block, for example, send 10 Bitcoin or IoTeX tokens from Simone to Giuseppe, right? If I have added, let's imagine this is a transaction, a valid transaction message, then of course the hash of this block changes. And at this moment, with this data, this block would not be considered valid. Because we cannot change the block number, we cannot change the data. The only thing we can change is the nonce. So if I change the nonce, 1, 2, you see that the hash changes, of course, because the data is changing. Of course, the chances that I can find a number that produces a hash that has exactly at least 4 zeros in the beginning is very low. If I do it manually, I could stay here days and weeks and can't find the number, the correct number. If I click the mine button, then the software behind this web page will start checking by brute force, basically all the possible numbers until it will find a hash that includes 4 zeros in the beginning for this data set. And if I click it, it will take, at this time it was very fast, it will take the number that together with the rest of the data will produce a hash with 4 zeros. So for our hypothetical blockchain, this is a valid block now. And I can propose it to the blockchain, to other blockchain nodes. If I've been the first one who found this number in this like competing mining process inside the blockchain. So if I'm the one who found it, the first one, I can propose this block. Other blockchain nodes will accept it if it's valid, so they can quickly verify that the hash of this data is correct. It's this one that I am proposing. And so I must have done some work, right, to find this number. And then eventually this block will be attached by everybody, by all the other nodes in the network, to their copy of the ledger because it is valid. And so eventually you will end up with a sequence of blocks where for every new block that has to be attached, all these nodes, all these miners will try to find the correct number that allows the hash of the block to be valid. And the first one will be the one that proposes the block, and all the other ones will accept the block and attach the block to the blockchain if it is valid. So how does it work, right? So if I have a block where I add the transaction, let's say transaction 1 and transaction 2 and transaction 3 in the first block, then I mine this block. Let's say I'm the first one who found the correct nonce, and then I propose this block and it gets attached to the blockchain by all the other nodes. Then somebody else will try to propose a new block with transaction 4, transaction 5, will compute the nonce to make it valid, will propose it, and it will be attached again, and so on and so forth. Other nodes will mine new blocks and attach them to the blockchain, and all the other and propose it to other nodes, and they will attach it to their copy, and so on and so forth. So what can happen is that at any given time, it's possible that different nodes propose a valid block at the same time. And so some part of the network will accept that block, some other parts will accept the other block. And eventually the consensus is reached, as I said, by the longest chain. So eventually the nodes will accept that copy of the ledger that has the maximum, like the longest number of blocks, valid blocks attached. And that one will always be the current valid blockchain. If I try to change something in a block, if I'm a miner and I want to alter a block, for example, this one, I decide to cancel this transaction here. So I delete it from my copy of the ledger. As you can see, this will invalidate all the future blocks because every block includes in a blockchain, not only includes the block number, the nonce, and the data, but it also includes the hash of the previous block. And so eventually when I mine a block, I generate a hash, and this hash will be included in the next block, so that if I delete a transaction from the history of the blockchain, then the hash of this block will change, which as a consequence will not match the hash of the previous block in the next block. And so the next block will become invalid in this blockchain. This means that I will have to mine the block that I've modified, but I will also have to mine all the next blocks in my copy of the blockchain. Why? Because if I propose this blockchain with only this block changed here, this will definitely be shorter than all the other blockchains that also included the other blocks. And also it will not be accepted. So I will also have to mine all the other blocks in the blockchain, in my copy of the blockchain, and then propose it to the rest of the network and hope that they will accept it. Of course, they will never accept it because mining is really a proof of work, and it's usually an expensive work because, for example, in Bitcoin, the hash that you have to find is supposed to include a large number of zeros in the beginning, which makes finding the nonce a very expensive in terms of computation power, a very expensive computation, which takes a long time. You have to be very lucky to find the correct nonce before any other else. And so meanwhile, you mine your modified block, and then you mine the rest of the blockchain. The rest of the network will have progressed with more blocks before you. And so eventually your blockchain will always be the shortest one, or anyway shorter than other blockchains in the network. And so this is what actually makes the blockchain immutable unless you have enough hashing power to be more powerful than the whole rest of the network and be able to mine block faster than them. Then you would be able to rewrite the history, produce a longer blockchain that's correct and valid, and then propose it to other miners in the network, and that one should also be the longest blockchain. So, and that's why eventually in Bitcoin or similar blockchains, you need to have the 50% plus one of the hashing power of the entire network to be able to like rewrite one block, and only the latest block, by the way. If you want to rewrite previous blocks, you must have more hashing power than 50% plus one. So basically, that's what makes the proof of work somehow immutable, right? So, so proof of work is just one way how you can, a decentralized network can select who is enabled, who is eligible to select transactions and propose a block. Proof of stake uses a different way. You don't have to compute a nonce. You will have to have a certain amount of tokens to have a certain probability to be selected by the network to propose a block. And delegated proof of stake uses even a different mechanism where those nodes that are allowed to propose blocks have been elected by other nodes in the network, and they are somehow trusted by the rest of the network, and they take turns into proposing new blocks. So eventually, one of the final concepts is mining. So why would somebody decide to do this work, run a server, mine blocks, and do this computation? That's because blockchain protocols embed a token concept. So the protocol itself defines an entity called token, and this token is used to pay or to reward those nodes that propose a valid block. And so honestly validate transactions and propose valid blocks to the blockchain, then they would receive a certain amount of these native token as a reward. This native token is BTC, for example, in Bitcoin. It's ETH on the Ethereum blockchain, and it's IoTeX on the IoTeX blockchain. And so it's a concept that's embedded into the protocol of the blockchain itself. So thanks to like these features of the blockchain, blockchains expose these interesting properties here: immutability, censorship resistance, meaning that because it's decentralized and there is no central authority managing the ledger, then there is no way to stop a transaction. There will always be a certain number of nodes in the network that will validate your transaction and include it in a block if the blockchain network is decentralized enough. Security, we will see soon why. That's based on the fact that blockchain uses cryptography to sign like transactions, and transparency, because by its nature, the ledger has to be accessible to everybody. Anybody can like run a node in the network. Anybody should be able to verify that the entire ledger is valid. And so the ledger is open to everybody, and anybody can, like, let's say, track whatever has happened from the very beginning to the very end of the blockchain. So thanks to all these things, a blockchain can act as a trusted, decentralized intermediary. So thinking only about this native token concept, that not only it's paid to miners, but it also can be transferred to different accounts in the blockchain. So thinking about this concept, only this concept, where you before needed a bank or a trusted intermediary that kept track of a ledger and prevented users to double spend money, when you needed this trusted intermediary like a bank to send money or any other asset from Alice to Bob, Now you can do it with the blockchain, so without an intermediary, and you can trust the blockchain that that person that's sending you value or that's sending you the native token, a certain amount of a native token, they're not trying to double spend that token, that amount of tokens, and they will not be able to cancel that transaction. And so you can really trust the blockchain network as an intermediary to like manage the transfer of value. So that's it, how you interact with a blockchain, right? So there is a blockchain out there, how we use it. So we use it, we want to use it to maybe transfer this native token. If we have any, if anybody else has transferred any to us, we want to transfer it to somebody else. Or we want to store data on this ledger because of its immutability features. That feature that it has, maybe I want to store something immutable on this blockchain, right? How I do it? How do it? Using wallets. So wallets are just clients of the blockchain network. You can, by the way, download the IoPay wallet, which is a mobile wallet for the IoTeX blockchain, but there are many other wallets that you can use with IoTeX, with Ethereum, and many other blockchains. I think MetaMask is the most popular one for desktop computers and also for mobile applications that also support IoTeX, also supports Ethereum. As I said, IoPay is the native wallet for the IoTeX blockchain, and it also supports Ethereum, by the way, and also other compatible blockchains. So what is a wallet? So a blockchain wallet is just a client of the blockchain, meaning that it knows how to talk to the blockchain. And a blockchain wallet is not more than just a storage of private keys. So a blockchain wallet is a very simple utility. It can generate a private key, it can store securely a private key, and it can talk to the blockchain, meaning it knows how to pack a message for the blockchain and how to use the private key to sign a message for the blockchain to accept it. What does this mean? It means that somehow you need to identify accounts in a blockchain, and who owns how many tokens, who is transferring tokens to whom. So you need identities. So in the blockchain, identities are identified by digital signature. This is a basic concept of cryptography where you can have a private key that you keep secret. You are the only one who owns that private key, possibly. And there is a public key that's uniquely connected to the private key that you secretly store. And this public key somehow can be used to make sure a message has been authored, so has been created by and only by the person that owns the private key that belongs to that public key. So seems a little bit twisted, but basically, if you have a private key and you want to send a message, the wallet will use the private key to make a digital signature on that message. And then anybody who wants to somehow verify that signature, they can verify the signature and recover the public key that belong to the private key that's made that signature. And that means that only the person who owns the private key that belongs to that public key is the one that can make that signature. And somehow you can identify the sender of a message, always assuming that they have kept the private key secret, and that's their responsibility. So basically, wallets are just digital signature builders. They know how to talk to a blockchain, and they know how to pack a message with a digital signature and send it to a blockchain. So blockchain wallets, they do not store tokens. They do not store any value other than the private key that you need to authenticate any action that you want the blockchain to take on your behalf. There exist graphical wallets, command line wallets, and also SDKs that you can import in your software and use them to sign messages and send them to a blockchain. And finally, for this introduction, what we use blockchains for. given that we can interact with blockchains, we can send these transactions to the blockchain. A transaction can, as I said, can be used either to transfer tokens, native tokens, so those tokens that are defined in the protocol, or they can be used to attach some payload of data that you want to store forever on the blockchain. So what we can use the blockchain for? Of course, we can use it to send data and value, or somehow when I say send, given how it works, basically it means transferring ownership. So there are these native tokens on the inside the blockchain, defined inside the blockchain that maybe I own a certain amount because somebody transferred me the ownership of a certain amount, and then I can sign a transaction that tells the blockchain to assign the ownership of these tokens, or like a certain amount of my tokens, to somebody else, to a different public key. So I can use it to send value transactions and data transactions, because as I said, I can also send a transaction that does not transfer any value, but only attaches a payload, or it does both. So transferring data and transferring value and data was introduced by the Bitcoin protocol. Smart contract is a new concept that was introduced by Ethereum. So basically, when they created Ethereum, they said, what if in the data of a transaction, like let's say in the payload, right, of the data, I use it to attach a bytecode, meaning a compiled version of a software, of an algorithm. So if I can do that, of course I can do that, right? But if the blockchain is also capable of reading and executing that bytecode, then this opens to a whole new world of possible things, because this software that has been sent in the form of a bytecode to the blockchain, like any other transaction, is just some data that is stored on the blockchain forever. And it's replicated in all the blockchain nodes. And if this blockchain is capable of running under certain conditions, this code, then basically you come up with unstoppable code. So software that is censorship resistant, that nobody can stop from running, and that nobody can alter what it does, because the code is stored on a blockchain. So, and that's why they're called contracts, because whatever the algorithm says it will do under certain conditions, that's what the blockchain will do for sure, if those conditions will happen. So you can trust a smart contract. And thanks to this, trust meaning you can trust nobody will change it. You can trust it does what it says it does. And you can trust nobody will stop the execution of a smart contract. And so what you can now build on blockchain, of course, you can build cryptocurrencies thanks to the ability to transfer the native token. But thanks to smart contracts, now you can also build custom tokens. So tokens other than the one that's defined in the protocol. You can define it in software and store this software as an application on the blockchain, and as a smart contract on the blockchain. And this new token can have a custom token economy that you can define however you want. Then you can create very easily gambling applications. You can, if you have already heard of NFTs, maybe you can build NFT gaming, card games, or you can use NFTs for authorization and many other different things. But eventually, what we have seen booming on the blockchain in the latest 2 or 3 years are DeFi applications. DeFi stands for decentralized finance. So smart contracts that run financial applications. For example, liquidity pools. Of course, we are talking always of cryptocurrency here. So liquidity pools of crypto tokens that can be used to do token exchanges, or lending and borrowing applications, or stable coins. And these applications run entirely on a decentralized network that anybody can trust. And always under certain conditions, of course, with some due diligence, anybody can trust. And there are no central authorities controlling how they work. Or if they want it to work or not work. So there is nobody who can do censorship on these applications. It's open to everybody. They are open to anybody to use and eventually to make money out of it. So I want to stop maybe for 1 minute and ask if there are any questions. Let me see if I can see the chat.
There were a couple of questions, and I tried to quickly answer as we're listening to you.
Okay.
But if you want, we can go through them.
No, if you have already answered, I would say let's go ahead.
Okay.
Because that time is short and we have a lot of concepts to talk about.
All right, cool. All right.
Yeah. So now that we have seen some concepts of the blockchain, and I understand that people that have never heard about blockchain or don't have experience, they can find these things very weird. So I definitely encourage you to dive deeper, learn more, because it needs some time to get familiar with these concepts and with the consequences of these properties that blockchain has. But then eventually, if you are a software developer, interacting with the blockchain and using it, it's extremely easy. The most important thing is that you understand the new possibilities and the consequences of blockchain properties. So let's move into something more advanced here, but also more interesting, I would say. Well, that's the blockchain, what's called the blockchain oracle problem. So from what you have heard until now, you may have guessed that blockchain is a self-contained and self-enforcing system. This means that when we send a blockchain, sorry, when we send a transaction to the blockchain, either we are transferring some amount of the native token of the blockchain, or we are attaching a payload of data that represents a smart contract execution. So, or we are doing some other things that are the smart contract deployment or some other side operations, but eventually either I'm transferring the native token or I am interacting with the smart contract, meaning I'm telling the blockchain to run a specific function in a specific smart contract that's been installed on the blockchain before. And I'm passing some inputs to this function, and I'm asking the blockchain to run that function with those inputs. So anything that a smart contract can do in a blockchain is just to rely on what's stored in the history of the blockchain. So eventually, the only things that the blockchain can work on are entities that have been created in the blockchain itself. So either the native token or other smart contracts or any abstract entity that has been defined into a smart contract. So in the end, the blockchain can only work, or let's say can only verify or trust things that have passed through the consensus of the blockchain itself. So if I'm telling a smart contract to swap a certain amount of IoTeX tokens for another token, the smart contract will be able to verify from the blockchain transaction history that I actually own that amount of tokens, and then it will do the swap, right? But this can be anything else, because the smart contract can even be a game or a complex application with its own defined concepts. So these concepts are always verifiable. They have been stored in a blockchain. They have passed through the consensus. They're tamper-proof, right? So this is a big limitation of blockchain. Another limitation is, so the blockchain cannot talk to the external world, cannot work on data coming from the external world, because it cannot trust that data. So as long as it's just a toy smart contract that does not involve any incentive, any value, then it can work on real world data. But as long as there is value involved or economic incentives involved, then anybody will be incentivized to also send fake data to a smart contract and somehow take advantage of whatever logic is in that smart contract. And so this is one limitation. Another limitation I want to mention is that blockchain is an expensive infrastructure, meaning it's a huge database and it's replicated in exact copies on thousands computers, ideally on a huge number of computers. So storing data in a blockchain is extremely expensive. I did not mention the concept of the fees. You can read about it, but basically when you want to write something to the blockchain, when you want to send a transaction and ask the blockchain to take note that I'm transferring some tokens to a different public key, then you have to pay a fee, and this fee is paid in the native token. And same when you run a smart contract or when you deploy a smart contract. It's basically all about storing data in a ledger. And then this is expensive, and so you have to pay for it. So it's definitely, blockchain is definitely not a good storage layer, data storage layer. And finally, another important limitation is that by its nature, blockchain is not private. So as long as you are sending public data to a smart contract, that's fine. But if you try to send data that by its nature, it's supposed to be private, it's sensible data, then you probably don't want to send it to a smart contract on a blockchain, because this would just reveal that data to the world, and you may not want to do that. Okay, so getting back to the Oracle problem, the question is, can I, for example, ask a blockchain smart contract something like this? Look, I own an apartment in New York. I have rented this apartment to somebody for $3,000 per month. I'm also getting consistent payments from this person every day for years. So please, asking to the smart contract, so sending a transaction to the smart contract with this data and asking the smart contract to lend me, for example, 100,000 IoTeX tokens for 1 week, then I will give them back. So if you are the developer of such a smart contract, will you give these people this? Would you lend these tokens to this person? Most probably no. Why? Because you cannot trust the data he sent you. How you can tell if he really owns an apartment in New York? How you can tell it's rented for $3,000? How you can tell? How you can like lock this value and make sure if he does not send you the tokens, then you will take something out of his value, of his real world value, right? That's very hard thing to do. So one possible way could be that there is an off-chain, centralized or decentralized, if you want, authority. In this case, most probably would be centralized, but could also be decentralized, that goes and verify by documents that these things are true, and then we'll send a proof to the blockchain that this is true. And the blockchain, the smart contract, is trusting this entity, either centralized or decentralized. And then maybe the smart contract can run this transaction and lend the tokens to the user. And if he does not give back the money with the interest, maybe there is some way that this off-chain entity can lock the value of this renting or whatever, right? Really an easy thing to do, I would say. Another example. So let's say I have used only 1 kilowatt of energy today in my apartment, and I'm asking the smart contract, please reward me for being eco-friendly, right? This is something definitely interesting. A smart city could deploy a smart contract on a blockchain and reward citizens with the smart city token if they are eco-friendly, if they can prove they've been eco-friendly, and then they can claim some sort of, I don't know, benefit or service from the smart city administration by paying with this smart city token that they received as a reward. This is something that seems to be a little bit easier because there are devices there are energy meters in your apartment that can count how much energy you have consumed. So it seems like a bit easier. This energy meter could send data to the blockchain. Do we trust it? Probably not, but let's keep in mind this detail, right? Another example, let's say I've slept at least 8 hours per night this week consistently for 1 week. And I ask a smart contract to reward me for sleeping well. Seems a bit weird. But imagine your boss, you are a software developer, and your boss, not because he cares that much about you, but he wants to make sure you go to work and with a fresh mind, so that you have slept well. You have not gone out like drinking or dancing or whatever every night, and then you only sleep 2 hours per night, and then you go to work and you cannot write decent code. And so the boss deploys a smart contract, and it will reward you if you can prove you have slept enough hours per day along a week. If you can prove it, again, there are simple trackers that you for sure know that can track sleep. Can we trust it, these devices, or not? Again, it seems something more doable here. So here we come to the concept of MachineFi. So the difference between the first example, and there are many other examples that are very hard to implement, because generating a proof in a decentralized way would be really hard. And generating a proof in a centralized way will still be hard and slow, but also it will bring all those problems that blockchain solved. So you will have a single point of failure. You will not have censorship resistance, right? You may have corruption. You may have interested people that don't want you to interact with that smart contract, right? So it does not make much sense. So we are interested into decentralized proofs of things, and implementing decentralized proofs with people, it's a bit complex. There is another concept that's called DAO, decentralized autonomous organizations, where there are people that collectively generate a proof, but this is not the case we are talking about. We're talking about MachineFi. This is another way to generate proofs in a decentralized fashion. And so MachineFi is this methodology, and it's also a platform that helps jumpstart machine networks in a decentralized fashion. These networks will incentivize the deployment of machines in the real world, would financialize the utility and data that comes from these machines, and it will eventually enable composable and transparent ways to build new applications. So before we go inside here, I want to spend a couple of words more about this concept. So why MachineFi? Because machines are, there is a saying that's code is low. This is related to blockchain. Code is low because blockchain made really code becoming the low. So it's whatever the code say, it's what will happen. And nobody can change this, right? So machines have the ability to run autonomously. You can program machines. So you can implement a protocol in a machine. And recently, with the development of IoT in general, regardless of blockchain, many hardware manufacturers are integrating special crypto chips into their boards or into their devices that help securely generating a private key. And when I say securely, I mean nobody can get access to that private key. So it's only owned by the device. And store it in a way that, as I said, nobody can get access to it. Then these devices can be also programmed with a firmware that is tamper-proof. So nobody can change the firmware. And then if I can build such a device that also has a crypto chip that can securely generate a private key and never leak it, meaning never leaking even to the firmware. So it's the chip that's making the signature. Then what I can do is I can write a firmware that does whatever it is the device is supposed to do. For example, monitoring your sleep, reading sensors, and running some AI, whatever it can do. And then generate the resulting message. In this case, it's generating a message that counts steps. So you see the message inside this JSON here that just send some number that is supposed to be the number of steps I've done with this device and a timestamp. that belongs to when this number of steps have been like counted by the device. And then there is a signature. Keep in mind, this signature, it does not belong to the blockchain. It has nothing to do with the blockchain. It's just a digital signature of the data that has been created by such a crypto device. So only this device or this step counter could have signed this data because of the properties of this chip that nobody can know what's the private key inside it. So let's expand this into something bigger. This is what a MachineFi type of application will look like in general. Blockchain on the right side, you see different blockchains here. IoTeX is this one, the green one. Blockchain runs the token economy. Devices send data, and this data is verifiable. It's verifiable because it's signed by the device using the crypto elements. So eventually, this data can enter another network that we need because of the limitation of the blockchain, because it's not privacy preserving, because it's not a good storage layer, and because it's also not a good computational layer. You cannot easily do complex computation or complex logic on a blockchain. And so eventually, you need another layer. And this layer, we call it at IoTeX WebStream. So WebStream for us is an off-chain infrastructure, an off-chain compute infrastructure that is a decentralized network. It implements a decentralized protocol, and it's in between the blockchain and the devices. And the role of WebStream is to collect data from devices, verify this data, so making sure this data is coming from the actual device it's supposed to come from, and finally generate proofs on top of this data. And these proofs are then ingestible by applications, by financial applications in a smart contract that then can run whatever token economy they are supposed to run based on the proofs that have been sent by this layer 2. It's called a layer 2 network. And you may notice that there are only proofs going into a blockchain smart contract, not the data, not the real data. So in the case of work to earn, of our example, what we are sending to the blockchain is not the exact data that that relates to me, how much I worked, when I did this activity, where did I go, all this information is not going to the blockchain. The blockchain is only receiving a proof that, for example, I worked 10 miles every day, say for 10 days or even just yesterday, just the proof that this happened. And this proof can be also as simple as just a yes or no, right? As long as this proof is sent to the blockchain by a trusted entity. So in our example, where we will, during these 3 days, we will show you actually this work to earn example. This is the simple architecture that we will use. We will use a simple hardware, which is an Arduino board, which I have here. If you're not familiar, you can go to www.arduino.cc, which is the website of this hardware builder. It's very popular, honestly, and it's great. They create these great boards that have huge value in hardware programming, in the educating people to hardware programming and specifically to IoT devices. And I create all these different types of boards. I have a lot of educational content. There is a huge community of people, of makers that use this board for different things. You can connect these boards to sensors, to motors, to whatever you want, and build interesting products. So we will use this board the Arduino Nano 33 IoT, because this one has that secure chip that I was talking about before. First, and second, because it has a nice accelerometer integrated in the board, so we don't have to connect it to anything else. And it can also count steps autonomously. We don't have to program anything. This accelerometer can just count steps. It's just a feature. And it's very cheap. So you can buy it on the Arduino website, also maybe on other websites for, I think, less than $20. So it's great for experimenting this concept of MachineFi applications. So that's the board. Then we will have the web stream network, but in our example, we are going to make it very simple. So it's not a decentralized network, it's a single node. So this node, we deploy it, we program it, and also this node is the one that sends transactions to our smart contracts, sending the proofs. And we will authorize the public key of this node in our blockchain smart contract so that we can trust that these proofs are coming from our own web stream node. So there is no decentralization in this example in terms of this network. And finally, we have the blockchain. So on the blockchain, we will have the smart contracts that make our MachineFi application. So basically the token economy. So there will be a DApp or a smart contract that will generate and send rewards to the owner of the device upon proving that they have worked according to our rules. And the rules are defined inside the web stream node. So let's see, it's much simpler than this slide looks like, probably. If you, you for sure are not familiar with these secure chips unless you have any special interest into IoT and embedded programming. But let's see how we can achieve trust, right, in our application. So I am the builder of the step counter. So what I do, I create a software for my board that uses the accelerometer to count how many steps have been done. So in our case, it's very simple and it's also very easy to fake. But of course, you can create an application, a firmware that's as complex as you want. You can use a GPS, you can use AI, you can use other sensors, body temperature, whatever you want. We will just read the steps from the counter, from the accelerometer. We make the firmware tamper-proof. There are embedded techniques to make a firmware tamper-proof so that once I've burned the firmware in the board, nobody can change it. And finally, my firmware would use the secure crypto chip on the board to sign the data. And as a final step, before I give this step counter in the hands of a user, I will take the public key that corresponds to the crypto chip private key. I will take the public key and I will store it on a blockchain smart contract that I keep for myself. No, not for myself, it's public, but I create it and I use it only for the purpose of listing the public keys of the boards that I've manufactured. And then finally, I give this board, I sell it or I give it in the hands of somebody. And I also have another smart contract on the blockchain that is intended to keep track of the public key of the owner, so the wallet address of the owner of the board, and the public key of the board I've given to this person. So basically, it's keeping track of the binding between a device and the owner of the device. I need this binding because eventually I'm going to reward the owner, not the device. By the way, this device doesn't even have a blockchain account, doesn't have a valid address for a blockchain. So I could even, I have no way even to reward the device, even if I wanted to. But usually a person, an owner could own many different devices, even in different ecosystems, and earn tokens from all of them. So it makes sense to bind one or more devices to a single owner account, and this owner is the one who can manage these devices in the different ecosystems and is the one that will eventually receive the rewards for whatever work they did or whatever work the device did, right? Finally, I've binded the device to the owner, and finally the owner can start using the device. In this case, they can start working with the device, and the device will keep sending this data, and this data will carry the digital signature of the board. Every data message will include a digital signature from the board, and these data messages eventually will reach the web stream network. In our case, it's just a single node infrastructure, and this node will receive the data, right? The first thing this node wants to do is to check the signature. From the signature, thanks to the properties of digital signature, the web stream node can recover the public key that made that signature. Then it can go to the blockchain smart contract where I stored all the public keys of my devices. If the public key is included, then because of the properties of the secure chip, that it stores securely the private key, so nobody else could have made that signature other than my board. And also because the firmware is tamper-proof, then if that public key is included into my registry on the blockchain, then I am sure 100% that data message has been created by my board, my firmware. And so it's not fake data. It's censored data, it's AI data, it's whatever I created in the board. And of course, I'm also storing this list on the blockchain. So it's extremely hard, almost impossible, for an attacker to hack the blockchain and like add a public key of a fake device or of his own device that he created to generate weird data or fake data, or even a software simulator public key, right? So nobody can do that because it's stored on the blockchain. Again, nobody can take ownership of a device because the binding of the owner and the device is stored in a smart contract on the blockchain. So much more secure than storing it in a centralized server. That said, the last step is about what's happening here after WebStream. So our off-chain compute infra has verified that the data is coming from my device, so it's trusted data. It may probably just store it somewhere in a database, in a decentralized database, or whatever the application requires. And then it will sit there, right? Maybe I can apply some complex IoT logic at this level if I want to, but eventually I will store this data or this information somewhere. Eventually, I can expect at some point this device owner wants to claim their rewards because she has been working for 1 week, 10 miles every day. So now she wants her rewards. So she goes to the blockchain, to the smart contract, and sends a transaction to the smart contract and says, I want to claim the rewards for the last week. At this point, the blockchain smart contract can emit events. It's not emitting anything. It's just storing this event in its own ledger. So the blockchain can emit this sort of event and say this wallet account, this blockchain account is claiming rewards for the last week. WebStream can monitor the blockchain. Anybody can monitor the blockchain. So WebStream can react to when it detects this event from the companion smart contract. And so it will pull the data required to reply from the database, compute whatever logic we want to compute. In this case, we will just count the number of steps the user has worked in the time frame. And then eventually WebStream will call back the smart contract in reply to that specific request and send the number of steps that the user has worked in the time frame. Could be, for example, something more complex. For example, WebStream could send also other information. For example, if this owner has worked in group with other people, if you have a GPS on the device, or if this owner has worked in areas, like in healthy areas, like in a forest or next by a highway, right? And maybe earn more if they work in a park or if they work in a forest. So you can implement whatever IoT logic you want here, and eventually send this information back to the blockchain. And keep in mind, you're not sending the data to the blockchain, but only the minimum required proof that the blockchain needs to run the token economy, to trigger the token economy. And then eventually the blockchain will receive this reply from the WebStream node and will somehow credit some balance of a custom token to this owner with some token economy that is specific to the application. Typically, you can have decreasing incentive token economy. So what the smart contract would credit you more tokens, for example, in the beginning, when you have just launched your application, to incentivize more people to join your ecosystem. And then these incentives may decrease. Given a certain amount of activity, the rewards may decrease with time. After you have bootstrap your ecosystem. But you can implement whatever logic you want. So here is how, like, just a bigger, closer look at how a message from this device would look like. So it's just a JSON message that includes the actual data message and then the signature created by the crypto chip. In this example, we have also added some metadata like the device ID and which is basically the public key of the device. What cryptography we have used to create this private key, what hashing algorithm we have used. So just some metadata, but we could just not use it. I mean, it's up to you to define what your device protocol, data protocol looks like. So this is the last, I think, 10 minutes. And I will use it to go through the actual firmware. Let me actually open it on our developer portal, so it's bigger. Okay. So this is, I think you're familiar with C or C++. So this is how you program such a board. You program it in C++. There is an IDE called Arduino IDE, and it's this one. It's very simple. You connect the board, and it's very simple to just select the board from the IDE, the serial port you connect it to, just compile the firmware and just flash it to the board. And it's really easy. So I will just go through the firmware because there is nothing too complex here because we have already explained everything. So the firmware for this board will just run a setup one-time function that runs when you power on the device. That's how these Arduino boards work. So the setup function will just send out some log to the console. We'll read the total number of steps we have stored in the flash memory just to keep track when the user shuts down the device. It will initialize the crypto chip, and that's just one single command. We are importing the library for this device, and it's this one. So we initialize the crypto chip. We make sure the crypto chip has been itself initialized with a private key. So again, we use the library. We initialize the Wi-Fi, not going into the details here because you can find this code everywhere on the internet. And again, it's just a library, a couple lines of code to just connect to your Wi-Fi network. This board has a Wi-Fi antenna, of course. There is a library that uses the NTP. It's an NTP client that can be used to read the time from the internet. And finally, there is a library that is called MQTT lib that is basically a client of the MQTT protocol. The MQTT protocol is just like HTTP. It's just a network protocol that is typically used by IoT devices to transfer data. We use this protocol and just initialize the library here. Eventually, we ask the crypto chip to tell us what's the public key that belongs to the private key as generated. And we use this as the unique ID of our device. That's what we store on the blockchain. We ask the device to tell us what's the public key because I just want to output this to the console and then use it when I want to register my device to the blockchain. So finally, these are minor details of the MQTT protocol, nothing fancy. It just expects you mention a path where you want to publish your data so that on the other side of the protocol, the receiver can somehow select the path they're interested to watch. So finally, that's what the device does. Into the loop function, we'll just read the steps from the accelerometer. The details of these functions are below, but they're very simple because they use basically the library, or just read the register into the device, but you find it on the internet. We did not invent anything here. So we read the number of steps in the accelerometer. Then we read the current timestamp from the internet using the NTP library. Then we build the message, meaning it's just a string concatenation here where we create, sorry, I wish I can open it. I've lost the presentation. Where we create this message here. So just a string. We have the number of steps, we have the timestamp. So we create that string. Then we ask the secure chip to hash that message. And then we ask the secure chip to sign that message. And then eventually we have the signature in our hands. And so finally, we call another simple function that builds a string that represents the JSON, the full JSON message, which includes the data message, the signature, the device ID, which is just the public key, and just some constant metadata into the message. And so eventually we have created this string into the MQTT message here. We print it to the log, and we use the MQTT library client library to just send the message over to our web stream node. Okay, delay 3 seconds and loop again. So this loop is called continuously by the device hardware. So we don't need like to create the loop ourselves. It's already managed by the device. So that's what the device does. Very simple. I want to show you the log of this device. So I have this firmware already on the device. So I reset the board. And so you should see the output of the firmware. So it's reading the last steps, total number of steps from the flash. We keep storing this total number in the flash each time we read the new number from the accelerometer. So it will initialize the secure chip, will connect to the Wi-Fi, gives me the local IP address of my Wi-Fi network, will sync the time with the internet, current timestamp. This one is read every time a new message is created. It's connecting to the web stream node. I have already a web stream node running here. And finally, it's outputting the public key just for me to make use of it conveniently when I want to register this device into my smart contract. If I move it, it will read new steps from the accelerometer and send the data to web stream. And here is the message it's sending. So it's sending this string here, which is exactly a message with the total number of steps. It's increasing, 162, 166, the timestamp when this reading has been made, and the signature of, this is the signature of the hash of this. typically when you do a digital signature, you do it on the hash of the data, because you usually, if you can even sign 10 gigabytes of data, you just hash and then you sign the small sides of the fingerprint of the data. It's like signing the data eventually because of the properties of the hash. And then there are some constant metadata. So the device ID, which is basically the private key, sorry, the public key. I'm actually using only 20 bytes of the public key to like invent this device ID. It's just like the serial number, right? And then some metadata. So this is what the device is currently generating and sending to the web stream node. I will stop here exactly at the end of the hour. But yeah, let's leave maybe, I know I went very fast. It's a lot of concepts, but it's 3 days, so you have time to get familiar. As I say, you can also ask questions to Discord or just prepare your questions for the next day. Giuseppe, are there any questions?
I've tried keeping up with the questions and provide everybody here with as much links as possible as you were talking. The last question that I haven't gotten to was just sent forward by Pritam, and he says, isn't censorship a major concern with Web3 apps?
Not sure what exactly Pritam means. I mean, censorship is a problem for centralized infrastructure because it's centralized. So there is a central authority who is controlling this infrastructure. Then this authority could decide on itself or on request of somebody else to just censor, sorry, to just cancel or just block any transaction, like block your account entirely and prevent you for doing bank transactions, right? The bank could do that. They do it, actually. They even close your account without any reason sometimes. So censorship is a problem of centralized infrastructures. Blockchains are decentralized, and there is no way for censorship to happen in an enough decentralized network, because you would have to stop or somehow block all the nodes, or anyway, the majority of the nodes of the decentralized network. And if it is very decentralized, and also the node who is running the node, anybody can run a node, so you don't even know who they are, it's just impossible. Censorship means that somebody sends a transaction and somebody else decides to just delete this transaction from the history ever, right? So preventing you to interact with the smart contract. So preventing you to sending tokens, right? So this is just not possible in block, or it's almost impossible on a blockchain. And so it's definitely not a concern with Web3 apps. It's an advantage of Web3 apps.
You can read the follow-up question, right?
Yeah. If we want to stop some malicious activity. So there is not any we. There is not any we in a blockchain network. There is a network, and it's decentralized. It's open to everybody. It's the responsibility of the smart contract builder to create a safe contract without bugs that can be exploited by a malicious actor. Of course, this is not always possible. So we have seen in the past bad events like the DAO. If you look for the DAO hack on the internet, that was an event where a malicious actor had stolen millions and millions of dollars from a smart contract on the Ethereum blockchain. This led to other problems where the blockchain forked. There were 2 Ethereum blockchains at that point, and they are still there, 2 different Ethereum blockchains because of that event. Basically, there is one Ethereum blockchain where that event has never happened. So they decided to censor, so to cancel that event from the history. Like all the miners agreed that they wanted to cancel that event. And so they did it. And that's Ethereum Classic. It's called Ethereum Classic. And then there is the actual Ethereum. That's the actual network that never deleted that event. So they were respecting the nature of the blockchain. And they did not those miners that did not agree with deleting that event. And so this is what can happen, but not that there is somebody who can just alone decide that they want to cancel something from the ledger. But yes, it can happen that a group of network maintainers do not agree with another group, and then the blockchain forks. There are two different versions of the ledger.
Cool. Yeah, and also, I mean, if anybody else has some questions, feel free. Professor, if you want to maybe say a few words, I will ask you to unmute.
Yeah, great. Thanks a lot. It's a great tutorial. Yeah, I look forward to the next one.
Yeah.
I think the students also learned a lot. Yeah,
yeah, it's a lot of new information for those students that are not familiar with blockchain. And it's actually a lot of information also for those who are familiar with blockchain, because this MachineFi, IoT, hardware, trusted data, verifiability of data, the off-chain compute network, it's all new concepts. So yeah, take it as an inspiration to learn more, I would say.
And
MachineFi is also very
I've also added a few links. If you guys scroll up in the chat, there is one link that goes exactly to where Simone's screen is now on the part 1 of the workshop that talks a little bit about the firmware. I mentioned the libraries that you will need just in case you want to proceed. And then other useful links on the Arduino store, so you can learn a little bit more about it. And yeah, any questions, just feel free to ask us on Discord or however else you want to reach out.
Yeah, maybe if there is another minute more, maybe this is an interesting question here. I'm not sure what you replied here. Just want to add something on top of what you have said. Does the proof depend on the centralized node? So in our example, yes, it depends on the centralized node, because we are creating a simple off-chain infrastructure where there is only one single node. And so necessarily we have to trust the proofs that node generates. And we do that because that node sends a transaction to our smart contract that brings the proof or brings the result of the working activity. And so that transaction is made with a blockchain address. That's the address of the node, of the WebStream node. And we have somehow authorized that address to call that function in the smart contract. That's the only address that can call that function. And that's the way we trust that single node, that single node, right? We trust the single node because we have created it, but we trust the reply because the reply is coming from the blockchain wallet that we have configured into our WebStream node. And so we are sure that reply is coming from our node. But for WebStream, you can have also, in the future, you can also have decentralized configurations for the infrastructure where WebStream itself is a decentralized network of nodes. And so this means that the IoT data is replicated into these nodes. And so before there is a proof sent to the blockchain, this proof must come from a certain number of nodes that have agreed on they run a consensus on the data they are creating the proofs on top of before they send the proof to the blockchain. So this is a more decentralized way of generating the proof. Yeah, with that, I think we really packed a lot of information. And yeah.
Cool. I will stop the recording and
yeah.